Disperse X6 considered energy inefficiency in Intel Optane DC persistent memory service. University of Central Florida, USA. Abstract: the Intel Optane DC persistent memory module AEP, which is the first commercially available non-volatile memory NVM product, offers comparable performance with DRAM while providing larger capacities and data persistence. Existing researchers that substitute NVM and DRAM or hybridize them are either emulator based or focused on how to improve the energy efficiency for writers. Unfortunately, the energy efficiency of the real AEP system is less explored. Based on real AEP, we observe that even though eliminating the DRAM-like refresh energy consumptions, AEP consumes significantly different energy at different performance levels. Specifically, requests with time intervals dispersed underperform in both performance and energy efficiency when compared with the case of requests without time intervals compact. This disparity and parallelism exploration potentials motivate us to propose Sprint AEP, an energy efficiency oriented scheduling method for AEP equipped servers. Sprint AEP fully activate adequate AEP to serve most of the requests by referring the right request and prefetching the hottest data. The remaining AEP will stay in ideal mode without low idle power to save energy. Besides, we also utilize the read parallelism to accelerate the sync and prefetching processes. Compared with the energy-unaware AEP usages, our experimental results show that Sprint AEP saves up to 26% energy with little performance degradation. Index terms: Intel Optane persistent memory, energy efficiency, scheduling. Introduction: loading all data into dynamic random access memories (DRAMs) is usually regarded as the last resort to solve storage bottleneck performance problems in the age when there are significant performance gaps between memory and storage devices. However, the exponential growth of application footprint challenges this DRAM-enabled method at various aspects such as the capacity, data persistence, and energy limitation. First, a maximum capacity of 256 GB per DRAM is far from expected capacity demand. Second, data in DRAMs is volatile, while the data persistence is usually considered as a default option for storage systems. This demand avoidably exacerbates the disadvantage of DRAM capacity limits. This is because persisting data to or loading data from the relatively much slower non-volatile hierarchies significantly compromise the performance benefits of residing them in DRAMs. Third, limited power budgets are unable to support the free scale of DRAMs, and as much as 40% of the total power consumed in a server attributed to DRAMs. 3 to 5. Many researchers are trying to address these issues in both micro and macro approaches. Micro-based strategies continue to explore potential of DRAMs from their physical internal organizations, optimizing DRAM energy consumption to mitigate the energy limitations and also helps to scale DRAMs to provide larger capacities. These methods 6 to 12 take DRAM physical structures into considerations and process all the memory mainly by only a part of the DRAM banks while keeping other banks in the energy efficient mode. Considering that DRAM onboard memory management units are usually black box to users, these approaches are difficult to implement. Besides, periodical refreshes for valid data in DRAMs still consume 13% of the total power even at idle state. 5. Micro-based approaches introduce non-volatile memories (NVMs) as a supplement to or substitute for DRAMs. Apart from competitive performance with DRAM, NVM devices provide lower standby power with data persistence feature, and more importantly, higher storage capacities. These advantages of NVM greatly satisfy the large capacity and high performance demand from large footprint applications, and make it a promising alternative to DRAM. However, existing research solutions employ publicly available NVM emulators or prototypes to investigate problems, such as limited write endurance 30 to 17, or the asymmetries of read and write operation in terms of performance or power consumption 60 to 20. As technologies evolve, the newly released commercially available NVM device, Intel Optane DC Persistent Memory Module AP21, creates new possibilities for system architecture. 3D X-point technology can offer near DRAM performance and disk-like non-volatility. A typical double processor Intel server can hold up to 12 AAPs, and the capacity of the AAP is 128, 205, 512 GB. The AAP server can provide a single storage architecture, where the function of memory and persistent storage are combined by only one medium. In confronting a massive amount of valuable information is sharply increasing data. 22. The AAP server enjoys brighter prospects. However, the noticeable problem is that the practical characteristics of the AAP remain unknown and thus worth to be explored in order to better align with high-level designs. Experiment with different access patterns and lots of tests. We observed that the inescapable energy consumption of the AAP can't be ignored. AAP shows significantly energy consumption differences at various performance levels, specifically requests with time intervals. Dispersed underperform in both performance and energy efficiency when compared with the request without time intervals. Compact. AAP also shows a great parallelism exploitation potentials. These findings imply that fully activating only a part of AAPs in server is able to handle the majority of requests most of the time. This disparity and parallelism exploration potentials motivates us to propose Sprint AAP, an energy efficiency oriented scheduling method for AAP equipped servers. As key value storage systems are widely deployed in data centers. 23 to 27. We develop our Sprint AAP with a simple key value storage system and evaluate with typical key value traces. To achieve high throughput, we employ a simple hash function to dispatch requests to all the AAPs, which is similar to the Dynamo 25 than for high energy efficiency. Usually Sprint AAP fully power on adequate AAPs to absorb the incoming request and powers on adequate AAP at best effort, and dispatches missed to remaining either AAPs. Moreover, Sprint AAP utilizes the parallelism potentials to compensate for passive performance degradation for standby AAPs and to boost data movement among different power mode AAPs. In summary, we make the following contributions in this paper. We conduct experiments on real AAP devices and finding opportunities to reduce energy consumptions for AAP-equipped servers. We take advantage of the parallelism exploration potentials to provide performance guarantees. We implement Sprint AAP on server with real AAP devices. Experimental results show that Sprint AAP saves up to 26% energy with little performance degradation. Table of motivation test configurations. Table to measure AAP powers. Background and motivation. In this section, we firstly brief the AAP product and then give experiment on server with real AAP devices under different access patterns to quantitatively show their energy and power characteristics. Finally, we explain our designs of a sprint. AAP is a high level of classified design principles. Intel Optane DC persistence memory modules. AAP, the newly released commercially available Intel Optane DC persistent memory module, named Apache Path. AAP provides DDR interface just the same as DRAM, and currently a dual processor Intel server can hold up to 12 AAPs. The typical capacity of an AAPs is 128, 256, 512 GB. Therefore, a server provides up to 6 TB. The 3D X-Point technology enables AAP products offer near DRAM performance and data persistence. This significantly closes the boundary between CPUs and storage levels. Besides the performance parameters, however, the energy consumption and parallelism capabilities of AAP are less explored. B. Access pattern and the AAP power mode, experiment configuration and method. Tab. I list the parameter of motivation experiment on the AAP server and we use a running average power level RAPL interface to measure energy usages in the DIMMs area. 13. To measure the AAP power, we set a test group and control group in the two processor servers, which is shown in tab 1. In detail, CPU 1 DIMMs area is set as the test group, and the CPU 0 DIMM area is set as the control group. The DRAM of both groups is the same, and the AAP only existed in the CPU 1's DIMM area. Through the NUMA and bypass DRAM method, the requests are sent to the AAP directly by comparing this test group and the control group. We finally obtain the energy consumption of the AAP. Workload patterns. As there is usually a time interval between two requests in the real world. 31. We plan to explore the influence to difference time interval of AAP. To resist the disturbance, the time interval between two requests is fixed during each test, and the request size is 4 KB in our test, as 4 KB is a typical size. Note that show similar result for other request sizes, such as 256 bytes or more significant. We send requests with different time intervals to simulate the heavy and light workload access patterns. Specifically, requests with time intervals are dispersed accesses, and requests without time intervals are compact accesses. We start from the 0 time interval and run a new test every 0.1 millisecond until the 1.6 millisecond time interval with random sequential write and read cases. Tap to list of the measured power of AAP is in watt. When time intervals between requests are long enough, AAP shows steady energy consumption in 1.91 watt, which means that AAP requires a static power supply. As time intervals becomes shorter, AAP consumes more power, ranging from 1.91 to 3.3 watt, and finally reaches its fully active mode in 3.64 watt under compact accesses. These energy consumption differences indicate that AAP energy consumption is tunable with different access patterns. The following subsection, the quantitative the relationship between access time intervals and performances. Performance and energy efficiency. The average response time of 4 KB request under 4 read and write mode. Performance and energy efficiency. In figure 1, we can see the average response time is closely related to the AAP power. The higher the average response time, the smaller the power of AAP. In general, the read outperforms the write. The shortest average response time is observed at the 0 time interval, and the average response time changes a little between 0.1 millisecond and 0.8 millisecond time interval. Then the average response time reaches a high value at the 0.9 millisecond time interval. As shown in figure 2, for example, the average input and output operations per second IOPS and A power under random write are introduced. As a function of the time interval, the left ordinate and right ordinate represent the IOPS and AAP power, respectively. the IOPS of zero time interval is 254,131. In general, IOPS decreases exponentially with the time interval. AP power has the largest value at the zero time interval and remains stable at 3.3 watts between 0.1 millisecond and 0.8 millisecond time interval. Finally, AP power descends until 1.96 watts, which is almost the same as ADR power. As shown in Figure 3, to figure out the efficiency, we analyze the number of requests the AP can address with only 1 joule as a function of the time interval. The value of the zero time interval 69.7 is too large to be displayed as is marked with a label. With the decrease of the time interval, the value descended quickly and then seems to be stable at 0. The shorter the time interval, the higher the efficiency. Real-time power and total energy of compact and dispersed access with the same amount of data. Compact access top and dispersed access bottom over time. In this article, we propose two concepts, compact and dispersed request. In detail, the request with the zero time interval are named compact request, and the request with the non-zero time intervals are named dispersed request. Figure 4 shows the compact and dispersed access with the same testing dataset size. Dispersed access starts with the active power T on, causing energy consumption to rise until time T end, and finishes with final energy consumption E this. On the other end, the compact accesses begin at T on with the peak power, and remains until T1, where the compact access have been finished with the execution time energy consumption E economics. Then the AEP becomes ideal and the cumulate energy curve slowly rises during the ideal period from time T1 to T end, finally ending with the equal time energy consumption E economy and plus E econ. Penalized potential. We have also tested throughput and power of the AEP under different threads to explore the parallelism. Figure 5 shows the throughput of AEP under different threads. With increasing of the thread, the throughput of the read improves significantly, whereas the throughput of write improves slightly and has a visible drop at 8 threads. Figure 6 shows the related AEP power. We can find that the read power is higher than the write power, which is the same as the throughput. In addition, the AEP power almost remains stable as the number of threads changes. In short, read can benefit from multiple threads, but the write can't. Motivation nowadays to guarantee timely responsiveness for different requests. Storage service providers usually keep all the data in the main memory. However, holding a copy or most part of the entire dataset brings significant challenges to the capacity, reliability, and the energy consumption of the main memory. Dynamic random access memory DRAM is always used as the main memory due to its high performance, but DRAM has met the memory wall. 32. Fortunately, AEP can offer near DRAM performance, disk-like non-volatility, and large-scale capacity. A typical double processor Intel server can hold up to 12 AEPs, and the capacity of an AEP is 128, 256, 512 GB. The AEP servers can provide a single-level storage architecture, where the function of memory and persistent storage are combined by only one media. However, parts of the real-world workload traces are mainly composed of dispersed requests, severe tens of megabytes per second, which can't fully utilize bandwidth of an AEP. Meanwhile, we should note that an AEP will run with high power when dealing with compact requests and lightly dispersed requests, simultaneous intervals, therefore naively distributing requests to all the APs of the server is not energy efficient. To address this problem, we can fully activate only one AP to address most of the dispersed requests by deferring to the write request and prefetching the read request. As shown in section 2, the working AP can handle these dispersed requests with little added energy according to the detailed time interval, and the remaining APs will stay in ideal mode with low ideal power to save energy. When one AP is unable to deal with the compact request, more AP will be fully activated. Finally, the default write requests will be synchronized to their corresponding ideal APs, which offers an opportunity to leverage the internal parallelism of the AP. In detail, as shown in section 2, we can read the default write request with multiple threads, which can significantly accelerate the sync process with only little added energy. And the parallelism can also be used in the prefetching process. Though we can't keep only part of the AP's standby with ideal power at present, the internal controller of each AP designed by Intel offers an opportunity to achieve this goal in the future. System architecture. As shown in figure 7, the system architecture of our Sprint AP consists of 3 parts: CPU, primary APs, and ideal APs. CPU is mainly responsible for distributing requests across all the APs. All the APs are divided into 2 parts: primary APs and ideal APs. Primary APs are fully activated to guarantee the performance, and the ideal AP are always kept standby to save energy until there is an either AP access. There is at least one primary AP, and the number of primary AP and either APs varies with the intensity of the workload. When the workload is too heavy for the existing primary APs, one either AP will be fully activated as an added primary APs. For convenience, we set a parameter 10% in our test to judge whether an either AP should be fully activated. Firstly, we fully activated an ideal AP for several seconds can calculate the rate of write and read throughput increment. If the sum rate of the write and read throughput increase can achieve archive alpha, this ideal AP will be kept as an added primary AP. Each primary AP responsible for up to m ideal APs, which is set as 3 in our test. Each primary AP is logically divided into 3 parts: AP cache, AP buffer, and local area. The local area stores the data that is originally dispatched to the primary AP. AP buffer will absorb the write requests that are originally dispatched to ideal AP, and data in AP buffer will be synchronized to each corresponding ideal APs. In this way, the originally dispersed write requests of ideal APs will be gathered into compact write processor. After the data synchronization, these write data will be logically moved to AP cache. In addition, we also fetch the frequently and recently accessed data from ideal APs to AP cache in advance. Those parts of the originally dispersed read request will be turned into compact prefetching processes. As the compact processes have a higher energy efficiency than the dispersed process, and the added energy of primary AP is negligible, more energy will be saved. Data organization. The index architecture of the storage system. For better data organization, we design an index architecture which is shown in figure 8. The first layer is hash function, which is a function of the key for key value request and decides which AP or request belongs to 25. The second layer contains the B plus trees, which only manages the data that are temporarily stored in the AP cache and the AP buffer. There are only metadata in these B plus trees, and each B plus tree corresponds to one ideal AP. The third layer contains the AP buffer and the AP cache of every primary AP. AP cache stores the data is most likely to be accessed, including the frequently and recently accessed data prefetching from the ideal AP and the clean data from AP buffer. AP buffer absorbs all the write requests for ideal AP by many rows, and each row corresponds to one ideal AP. The first layer is the final data storage area, including the ideal AP and the local areas of the primary APs, and each area is organized by the internal B plus tree. When a request comes, it will be first processed by the hash function and then sent to one of the primary AP. If the request is originally dispatched to one primary AP, it will be directly addressed by the local area of the primary AP. Otherwise, the request will visit the B plus trees of the AP cache and AP buffer. If the request is write process, it will be written into its corresponding log in the AP buffer. Otherwise, we will read the data from the AP cache, AP buffer, or the corresponding either AP. When an either AP is read, we will start the prefetching process, which introduced in the next subsection. Due to the limited space of AP buffer, each row will be synchronized to its corresponding either AP when the row size reaches the threshold 80% of the AP buffer in our test. As the read performance will benefit from the parallelism, we will synchronize these rows with multiple threads to multiple either APs. In this way, the synchronized process will be significantly accelerated. Besides, we use the key value storage system in this article, and the metadata of each key value entry is designed as key value address, pointer, hotness, flag. The key represents the logical address of the request in our implementation. The value address represents the physical address where the value is stored. The pointer is reserved for the prefetching data chain. The hottest means the access popularity. The flag means whether the data is dirty, flag 1, or not, flag 0. For the B plus trees of the AP cache and the AP buffer. And the flag also means whether the data has been cached, flag 1, or not, flag 0. For B plus trees in either APs, note that B plus tree in the local area primary AP only needs key value address pointer. C. Prefetching. To further request the energy consumption of either AP, we propose an energy-aware prefetching algorithm. Since the AP buffer can temporarily address the write request for either APs, our domain concern is about the read request. We intend to design prefetching algorithms to reduce the read access for either APs. Very roughly, first we will divide the data of AP cache and either APs into different HAN levels, respectively. The higher the HAN level value, the larger the visit probability is. Thus, the hottest data in either APs will be prefetched to AP cache when there is primarily AP cache miss. Figure 9 shows the sketch of prefetching data from either AP. In the beginning, we will initialize a HAN range list HRL cluster based on the B plus tree on the either AP. We will also initialize a cold range list CRL cluster based on 3 B plus related to the AP cache and the AP buffer. The largest HAN level value HRL cluster and the smallest cold level value in CRL cluster are named HMax and HMin respectively. To simplify the statistic, we impose certain limits on the HRL and CRL clusters. First, the smallest high-level value in HRL cluster should be larger than H-mean, and the largest cold level value in CRL cluster should be smaller than Hmax. Second, two clusters only record the metadata with flag equals 0. To improve prefetching efficiency, we divide the HRL-CRL cluster into several up to 10 HRLs, CRLs, every CRLs, constructed with LRU. The hot level value is sequentially incremented from HR1, CR1 to HR10, CR10. When a primary AP miss happens, we will fetch data from the corresponding idle AP, and a prefetching process will be triggered. First, data will be prefetching with multiple threads from the head of HRL10 to AP cache. If there isn't enough space in the AP cache, data CRL1 will be evicted. When HRL10 has been traversed, we will move on to the sequential chain HRL9 if the HR9 is still higher than CRL1, and so on. Otherwise, the prefetching process will be stopped. Besides, we should note that frequent and massive data migration is likely to cause dramatic fluctuations. To this end, we set a threshold for the prefetching size, which is 1/20th the size of the AP cache, and our results show that there are only a dozen of prefetching processes, and the related energy is negligible. To guarantee the consistency of all the B+ trees, we record the metadata of the eliminate data, which will be synchronized to the corresponding idle APs when there is an idle AP access. Evaluation result configurations. Table 3. The configuration of our observation test. We evaluate our Sprint AP on real AP server, which has been shown in tab 3. This AP server put 128 GB AP on the CPU DIMMs, and we run our test on CPU 1 and the 4 APs and NUMA without accessing the DRAM. The Yahoo Cloud Serving Benchmarks YCSB is an open source specification, and the program suite for evaluating the retrieval and the maintenance capabilities of computer programs is often used to compare relative performance of NoSQL database management systems. In our test, we use a C++ version of YCSB, which has low cost. Unless otherwise noted, the size of the key value request is set as 1 KB. The distribution mode of a request distribution is set as zip FIAN, and we use 20 threads to distribute request. As shown in tab 3, step 4, we choose two representative YCSB workload traces, YCSB-A and YCSB-B, and make a new YCSB3 traces represent 3 different write sensitives. The time intervals means the extra time we add between two requests. Therefore, 3 original traces, YCSB-A, YCSB-B, YCSB3, are defined as high density traces with 0 time interval. 3 traces, YCSB-AT, YCSB-BT, YCSB3T, are defined as low density traces with 50 microsecond time intervals to simulate the real-world traces. To evaluate the performance and energy consumptions of our Sprint AP, we set 3 configurations for comparison. Standard 4 AP are all powered on as a small distribution key value storage system to address requests without any power management policy. Sprint AP 4 AP are managed by our Nobel system scheduling scheme to save energy with little performance degradation. Sprint AP method without prefetching algorithm. Sprint AP parallel. Sprint AP method without using the read parallelism with sync and prefetching. B. Analysis on low density workload. According to the record, Sprint AAP only full active on one primary AAP when dealing with three low density traces YCSB-T, and the remaining three AAP are all kept with idle power most of the time because of the IOPS of YCSB-T is far away from the maximum bandwidth of the AAP, and one primary AAP is enough. Figure 10. Number of the read times for AAP. Primary AAP for standard mode. Ideal AAP for sprint AAP. Under different low density YCSB-T traces with 20 GB data. First, energy consumption analysis, as shown in Figure 10 and Figure 11, will record the number of read times, the execution time for the AAP. The first AAP for standard mode, an ideal AAP for sprint AAP. Under different low density YCSB-T traces with 20 GB data. In detail, all the AAPs shared execution time for the AAPs. The first AAP for standard mode, an ideal AAP for sprint AAP. Under different low density YCSB-T traces with 20 GB data share the similar number of read times in the standard mode, and we take the AAP as an example because the number of read times for ideal AAPs are largely reduced in the sprint AAPs. We mainly focus on the read access for one ideal AAP. The read time of sprint AAP contains the free fetching time. In Figure 10, compared to standard mode, it is clear that sprint AAP can significantly reduce the number of read times for ideal AAP. This is because AAP cache and AAP buffer can act as a large read cache for whole storage system in sprint AAP. In detail, sprint AAP work and pre can reduce at least 96% of the number of read times. Furthermore, sprint AAP can reduce about 99%. Sprint AAP performs better than sprint AAP pre, as more read requests of either AAPs will be addressed by the primary AAP through prefetching. In Figure 11, compared to standard mode, sprint AAP reduced at least 95% of the execution time because lots of time has been wasted by 50 microsecond time intervals in the standard mode, whereas sprint AAP pre can address most of the disperse requests by only one fully activated primary AAP with little added energy, and then gather these dispersed requests into compact requests by sync for write and prefetching for read. Thus, the idle time of remaining AAPs are extended and more energy will be saved. The write time of the sprint AAP is almost the same with sprint AAP. Sprint AAP is almost the same with the sprint AAP pre, as the write is unaffected by the prefetching. We can find the difference of the read time is small between the sprint AAP and sprint AAP WO pre, though there is noticeable difference for the number of read times. This is because each prefetching operation fetches a chunk of data from one idle AAP in compact mode, and there are only a few dozen prefetching operations. In detail, we can also find that the number of sprint AAP is smaller than sprint AAP WO pre under the YCSB-T, but larger than sprint AAP WO pre under YCSB-3T. This is because the effect of prefetching is in direct proportion to the proportion of read. According to the Tab 2 and Tab 4, 4 AAP of the standard mode work at 2.8 watt all the time. For the sprint AAP, when this stage and prefetching happens, all the 4 AAP are Figure 12. Total record time energy for AEPs for different configuration under different low density YCSBT traces with 20 GB data. Kept in the peak power 3.64 watt the rest of the time. Primary AEP works at 2.8 watt and the remaining 3 idle AEP works at 1.91 watt. Therefore, as shown in figure 12, we calculate the total record time energy of 4 APs for different configurations under different low density YCSBT traces with 20 GB data. Compared to standard mode, Sprint AAP WP can save about 26% energy. Sprint AAP consumes almost the same energy with Sprint AAP WP as they have the same read, write, and idle time. There is no difference between different workload traces because lots of time has been wasted by the 50 microsecond time interval, and the pure execution time only accounts for a tiny fraction of whole run time. Performance analysis. Performance comparison under different low density YCSBT traces with 20 GB data. Performance analysis. As shown in figure 13, we tested the performance of 3 configurations under different low density YCSBT traces with 20 GB data. Whether write or read, Sprint AAP slightly outperforms the standard mode. The reason is that Sprint AAP can easily gather dispersed requests into compact requests to improve the performance by the primary AAP can when the IOPS and IOPS YSBT is far away from the maximum bandwidth of the AAP. In detail, for write, Sprint AAP absorbs dispersed write request by the primary AAP and then synchronize these data to the related idle AAPs in compact mode by 3 parallel threads. For read in Sprint AAP, AAP cache and the AAP buffer can act as a large read cache for the whole storage system. Besides, for Sprint AAP, dispersed read requests can be turned into compact prefetching requests to increase the read performance further. This is no difference between the different workload traces. There is no difference between the different workload traces because the pure execution time only accounts for a tiny fraction of the whole runtime with a 50 microsecond time interval, and the throughput has been limited by the 50 microsecond time interval. The effect of dataset size, as shown in figure 14 and the figure 15, we also calculate the total energy of the 4 AEPs and record the performance for different configurations under YCSBT AT with different data size, which shows the same pattern. Total record time energy for AAP under the YCSBT AT with different dataset size. Performance comparison under YCSB AT with different dataset size. Analysis high density workload. Under high density workload traces, Sprint AAP fully activates 3 primary AAP under YCSB A and B, 2 primary AAP under YCSB 3, because one fully activated AAP can't guarantee the performance, and the detail has been described in section 3. Total record time energy of the AAP for different configurations under different high-density YCSBT traces with 20 GB data. Energy consumption analysis. As shown in figure 16, we calculate the total energy of 4 AAPs of different configurations under different high-density YCSBT traces with 20 GB data. Compared to standard mode, Sprint AAP can save about 7% to 70% energy because Sprint AAP fully activates 3 primary AAP under YCSB A and B, 2 primary AAP under YCSB 3. We can find the standard and Sprint AAP consumes the least energy under the YSB B because the read ratio of YSB B is the largest, and the AAP performs a better read throughput than write. Performance analysis. As shown in figure 17, we compare the performance of different configurations under different high-density YCSB traces with 20 GB data. We can find that the write throughput of standard mode is higher than Sprint AAP because the compact request distributed primary AAP has already reached its maximum bandwidth with B+3. Extra requests of an either AAP will exceed the maximum bandwidth and result in write performance degradation, whereas Sprint AAP shows almost the same read throughput with standard mode except for YSB3. This is because the read ratio is the smallest YSB3, and numerous write requests have reduced the request cache function of AAP cache and AAP buffer. But the read throughput is still the largest under YSB because of the largest read ratio. Sprint AAP always show a better read throughput than Sprint AAP pre, as the prefetching algorithm really works. Performance comparison under different high-density YSB traces with 20 GB dataset. Ratio performance in Figure 18. Ratio performance improvement under different high-density YSB traces with 20 GB dataset. To figure out why Sprint AAP fully activates 3 primary AAP under YSB A and B. 2 primary AAP under YSB 3, Figure 18 has been introduced. Figure 18 shows the ratio performance improvement under different high-density YSB traces with 20 GB dataset. The x-x plus 1 write and read means the ratio of throughput improvement of write and read when the system fully activates x plus 1 primary AAP based on x primary AAP. As shown in section 3, we set a parameter alpha, which is 10% in our test. In the sum of the x-x1 write and x plus 1 read can archive alpha. Then Sprint AAP will fully activate x plus 1 primary AAP. As shown in figure 18, Sprint AAP will fully activate the 3 primary AAPs for YSB A and B, and primary AAP for YSB 3. The effective parallelism. To evaluate the effect of parallelism, we test Sprint AAP and Sprint AAP parallel under all the YSB traces. First, as shown in figure 19, we evaluate the effect of parallelism under different high-density YSB traces with 220 GB data. The effect of the parallelism under different high-density YSB traces with 20 GB data. We can find the utilization of parallelism can significantly improve the performance. In detail, Sprint AAP outperforms 13% to 68% of 23.7% to 14% than Sprint AAP parallel on write and read respectively. Because we read the AAP caches with multiple threads to accelerate the sync process with only a small increase in memory. We read the hot data in either AAP with multiple threads to accelerate the prefetching process. We also evaluate the effect of parallelism under different low density YSB traces with 20 GB data, which is shown in figure 20, different from the result under high density YSB traces. The parallelism can only bring a little improvement in performance. This is because throughput is mainly limited by 50 microsecond time interval. Figure 20. The effect of parallelism under different low-density YSB traces with 20 GB data. Rated work, energy savings method of DRAM. To reduce the energy consumption of DRAM, many methods have been proposed. For example, they are tuning some banks of DRAM into low power mode according to request interval 6,7, processing all the main part of the DRAM, reducing the DRAM refresh rate to 1011, reducing the activation memory activation energy by scheduling the order of request, and so on 34 and 35. Although there are many energy saving schemes for DRAM in academic, the majority of them do not seem to actually promote industrialization. This is because chip bank of the DRAM is difficult to control, and data reliability and capacity of DRAM are always problems. First, the energy saving method of NVM. The energy-saving method of MVM usually save energy by organizing the data allocations of hybrid DRAM and MVM memory 30 to 17, 37, and 38. And some methods mainly focus on consistency and performance. Not the energy Article 16 proposed energy-aware persistence principles. Save energy by modifying the logging method of single MVM devices. Article 37 save energy by performing data allocation to different memories and task mapping to different cores. Article 38 uses DRAM to store the data with higher local I/O activity, while cache data with lower activity is placed into MVM to save refreshing energy. Most of the methods only focus on high write energy and latency, and the read energy is always ignored. System and product of MVM. The excellent characteristics of MVM have attracted extensive interest of industry and academia. 18. Academic researchers have proposed systems such as Softport 19, Petron 38, and Fodos that incorporate MVM both as memory and storage. Meanwhile, database vendors like SAP, Microsoft, and Aerospike have raced to announce MVM-based product 2041-42. However, these systems and products do not solve the energy consumption problem of MVM. Conclusion. In this paper, we observed that labeling scattering data to all AEP is energy efficient, and an AEP can obtain the highest energy efficiency when dealing with a compact request. Therefore, we propose an energy efficient AEP scheduling method named Sprint AEP. Sprint AEP fully activates only parts of the AEP to absorb all the request and dispatches misses to the remaining idle AEPs. Thus, the write request of the idle AEP will be temporarily stored in the fully activated AEPs, and finally synchronized to idle AEP is a compact mode. Given a compact prefetching algorithm for idle AEPs, most of the read requests can be addressed by fully activated AEPs. Therefore, all the write requests and most of the read requests of the idle AEP can be gathered into compact requests for better energy efficiency compared with named AEPs usage. Our experimental results show that Sprint AEP save up to 26% energy with little performance degradation. This work was sponsored by the National Key Research Development Program of China, the Creative Research Group of National Science Foundation.